Try this experiment. Take two bowls, fill one with ice water and the other with water that's comfortably warm. Now plunge one hand into each bowl at the exact same time. Our skin is incredible at detecting immediate danger, but it makes for a terrible scientific instrument. Biology is wired to sense the change in thermal energy compared to what it just felt, rather than giving us a fixed baseline reading. To see this flaw in action, pull both of your hands out and immediately plunge them into a third bowl filled with water resting exactly at room temperature. Your sensory processing gets completely confused. That exact same water will feel surprisingly warm to the hand that was just freezing, and shockingly cool to the hand that was just in the warm bowl. Our sense of touch is strictly a relative gauge. To survive extreme environments and conduct accurate science, humans had to invent a completely objective, numerical system to measure heat. At its core, temperature is a measure of kinetic energy. It tells us exactly how fast the microscopic, invisible molecules inside an object are vibrating and moving around. To communicate this energy, we created standardized languages like the Celsius scale, setting ice formation at 0 and steam at 100. The Fahrenheit scale looks at the same reality, placing those milestones at 32 and 212. Then there's the Kelvin scale, used heavily in physics. It introduces absolute zero, the theoretical limit where all molecular movement comes to a complete stop. This table shows the standard conversion formulas scientists use to map these numbers. Because these scales are fixed, researchers can seamlessly translate data between them. Agreeing on a shared math was the essential first step. Once the numbers were locked in, we could engineer physical tools to capture the actual data. The early liquid in glass thermometer was our first reliable bridge between abstract math and the physical world. It relies on thermal expansion. As the trapped liquid absorbs heat, its molecules vibrate violently, needing more space. Connected to a narrow capillary tube, that expanding volume is forced up, creating a readable line against a numbered grid. While early models relied on toxic expanding liquids like mercury, modern safety standards have largely pushed us toward using digital microsensors instead. By harnessing the laws of physical expansion, early engineers managed to take the invisible kinetic energy around us and force it to reveal itself right before our eyes. Notice the design in this diagram of a clinical thermometer. To accurately capture human body temperature, it has a tiny kink in the glass tube just above the bulb that mechanically traps the peak reading. Compare that to this illustration of a laboratory thermometer. It lacks that kink, requiring precise eye-level alignment while continuously fully immersed in a volatile substance to get an accurate number. When we need to measure extreme industrial heat or scan for fevers in an infectious environment, physical contact simply isn't an option. Infrared non-contact thermometers bypass thermal expansion entirely. Instead, they scan the invisible heat radiation actively emitting off a surface to instantly generate a safe reading. There is no single universal tool for tracking heat. We specialize our hardware to ensure our readings remain accurate across drastically different physical environments. These standardized tools give us the power to map extreme anomalies, like the lethal cold recorded by researchers stationed deep in Antarctica. This diagram illustrates a U-shaped maximum and minimum thermometer, which meteorologists use to track absolute daily highs and lows. This specific data lets us build the predictive models we rely on for global weather. That exact same precision dictates our modern infrastructure, allowing us to safely store delicate vaccines and execute highly sensitive chemical engineering. By swapping the biological guesswork of our skin for a fixed numerical system, we gained a way to observe the energetic state of matter across the entire planet. Mastering these measurements is what allows us to manipulate our environment, ensuring we can sustain life in conditions our own bodies could never survive without help.